Hello everyone. Today, our group will be presenting the seismic interpretation with Bundi case study using the Petrol software. So, before we start our presentation, we would like to introduce ourselves first. So, we start with me. Hello, my name is Nur Elmina Najmuddin bin Khairul Anwar.
Hello, my name is Nur Elena Diravinti alias.
Hi, my name is Sharifah Nazata binti Said Zari.
So, now we'll proceed with the presentation for our group. So, in this presentation, there are a few content that we include. The first one is the overview of the Bundi field, the project outcome, the project workflow, the methodology, seismic stratigraphy, discussion on finding the map, and the last one is the conclusion that we get from this project. So, overview of the Bundi field. So basically, Bundi field is a northeast part of the Malay Basin, and the early exploration activities within the basin was done in 1980s. The Bundi Field lithology is mostly consists of sandstone, and Bundi Field is located approximately 270 km north-northeast of Kemaman Supply. There are two wells that is being used to study the deeper subsurface of Bundi Field, which are Bundi 1 and South Bundi 1 well. The Bundi 1 White Cap is a well drilled at approximately 280 km north-northeast of Kemaman Supply Base, whereby the South Bundi 1 was in the exploration well drill, which is located around 275 km north-northeast of Kemaman Supply Base. Both well data that were produced by Bundi 1 and South Bundi 1 well, showing both well were gas filled. Even though Bundi gas field is located directly above the oil generating kitchen, there is a very little evidence showing occurrence of oil in the overlying structure of Bundi on the eastern margin. Bundi and South Bundi structure were formed by a combination of structural events occurring at extensional and compressional phase of a structural history of Malay Basin. The early extensional phase during Oligocene gave rise to the formation of half graben, and the later compressional phase of the Malay Basin is the structural inversion and east-west orientation of Bundi South, Bundi West, Bundi anticline, and the formation of fault band. Fault is also associated with the tectonic movement of the Bundi field. So here we can see where the South Bundi and the Bundi were located. It is, we can say that it is near to Terengganu and near to the peninsula of Malaysia. And Bundi and South Bundi well is located side by side to each other. So the project outcome that we get from this project, the first one, we are able to evaluate the geological structure subsurface in the Bundi field. This project contributes further understanding of the development and exploration in our area of study, and we, the student, are able to generate the subsurface map by correlating the seismic data and the well data from the Bundi field. Students are able to generate time and depth domain map of top F horizon, and we are able to produce the seismic well tie between the 3D seismic data well and the well data from Bundi and South Bundi gas field. The last one, we are able to do the horizon and fault picking and the interpretation based on the geological parameters of the South Bundi and Bundi well. So here is our project workflow. We start with the petrol installation in the first 3 weeks, and then the methodology, we import the seismic data, the well data, and the well top. We do all this project in the lab session with our graduate assistant. And as we can see, the submission is on the week 12. So now we move to the methodology. So we start with by import all the seismic data of the Bundi into the Petrol software. And after we have import all the data, we import the well logs that were including the well head, the deviation, and also the logs. After import all the data, we make the sonic log calibration using the SWT dialog box. And then we do this well seismic tie correlation, which we can be applied from the well log and the sonic log calibration. After the well seismic tie correlation, then we do the synthetic generation the purpose we do the synthetic generation is to get a better correlation with the seismic well tie. Then we move to the horizon picking of the top F, which the horizon picking, by doing the horizon picking, we can determine the horizon from the well data and complete the horizon picking throughout the line. We make it inline and the cross line. After finish doing the horizon picking, we are doing the fault picking, and for doing this, we need to choose whether we make it inline or S-line, because it is depends on the fault plane, and the picking must be perpendicular to the fault plane. And after doing the horizon picking and the fault picking, then we move to the surface map, which we generate the map using the seismic horizon data and the well top of the top F, and we create in time domain or two-way time and adjusted well marker. Then the velocity model, it can be generated by seismic surface and well top data. After doing all this step, then we can obtain the time domain map and the depth domain map. And the last one is the result and discussion on the finding of the map generated and also the seismic stratigraphy of the Bundi and South Bundi well. So now I'll pass the floor to Alia Nadira.
Okay, thank you, Elmi. So let's move to the seismic integration. So the first one, we move to the analytical website. Okay, next slide, please. Next slide. Okay, for this analytical website, so as you can see here, the coordinates of Bundi 1 and South Bundi, it's really close to each other. So the first one is sedimentary reflections at top F horizon. So the reflection configuration is parallel. Reflection continuity is low to very low. Reflection amplitude and frequency is low. Both are lows. And the reflection termination, as you can see on the screen here, in the yellow circle, there are two, which are top left and down left. Top left is on the top and down left is on the down side. So the phase of the waveflight is minimum phase. Later on I will explain you further. Polarity of the waveflight also I will explain you further. It is negative. The waveflight shape is vertical and the central frequency is 25 Hz. Next. Okay, well seismic time. So this is what Elmi has explained just now. The well seismic tie is to relate features from well data to peak and trough on seismic line, which is passing through the well location, and also to relate some features on the seismic well tie. It is very crucial to develop depth from well data to time relation in seismic data using checkshot data from from sonic log. So from the combination of sonic log and density log, so we can produce the seismic time. Okay, next. Okay. Seismic interpretation of synthetic well tie. So this is after we relate to both sonic log and also density log, we can generate the synthetic well tie. So the figure shows that the section for synthetic well tie is empty due to seismic error. So the seismic line should be presented on red arrow actually, but because of the error, so we cannot show the synthetic well tie. Okay, next. Okay. The next one is seismic stratigraphy. So before we start horizontal picking, we have to identify which line in seismic well tie that is represented top F horizon at Bundi 1 and South Bundi. So this one in seismic section at X line 3060, as you can see here at the left side is for Bundi 1 well, while at the right side is for South Bundi 1. Both are for top F horizon. So you can see here, this is clearly the triangle is the well. It's lie on the blue line. It's clearly can be shown in the Bundi 1 well, but it's quite confusing here at South Bundi 1. So we still pick the blue line because it is near to the blue line here. because both Bundi 1 and South Bundi are related. So we pick for top F horizon for both. So next, next is reflection pattern on seismic well site. So what we can see, what is the reflection pattern that actually we can observe from what we have done. So at the left side, you can see here the picture here in inline 385. There is the chaotic seismic signal here. So it's quite difficult to pick the horizon. Two yellow dots here. It's quite difficult to connect both two yellow dots because of the chaotic seismic signal here. So at the right side here, you can see it's like at line 3060. You can see that the distribution of seismic here is parallel, but it's a little bit inclination there to the north. You can see here. And then the reflection continuity at the left side in the circle, you can see it's continuous, while at the left side, at the right side here, you can see it is discontinuous, like it's there gap here. Okay. Next. The next is about seismic stratigraphy, still seismic stratigraphy here. So at line 3210 here, the yellow line here represents horizon peaking. So as you can see here, the horizon peaking is passing through the trough. So that's what I explained here. The polarity is negative. And first thing first, we do manual picking, and then we proceed with seeded to the outer track when doing QC, and also to connect to horizon with when there is a chaotic seismic signal there. And the spacing between X line and inline is 50 milliseconds. Okay. And at the right side here is the horizontal picking on 2D windows. This is the completed one, X line and inline here. And then next we move to the seismic geomorphology, the application of horizon slicing. So after we have done with horizontal picking, then we proceed with the production of time slice map. So here is at Z equal to -1600. You can see here the picture shows some geomorphology features, such as in the green line here there is fault, while in the blue circle here is channel. So after that, we use this information to find the geomorphology at seismic line on the interpretation window. So this is like a brief idea where to pick the fault and also to find where the channel is. Okay, next. Okay, the next one is after we get the brief idea about where the fault is, where the channel is, then we do fault picking and interpretation. So here is the fault terminology. This is the trough, this is heave, the stratigraphy is separation, and also the fault. So to pick the fault on interpretation window, firstly we have to identify where to pick the fault, like what Elmi explained just now, whether it's on X line or inline. So using the information that we get from the time slice map, fault must be perpendicular, which is mean that 90 degrees to the fault plane, which means that if the fault parallel to the inline, then we do fault picking on X line. Okay, fault must show at both inline and X line. Therefore, we have to be careful to pick and make sure to pick only the line which is perpendicular to the fault only. Okay, next. Okay, the next one is the identification of fault in seismic. So here is for an interpretation to be internally consistent, fault must tie on intersecting line. So as you can see here, the blue line here is tie, and the dotted pink line is the fault. Okay, the red line here is the horizontal picking. So this is what it's mean by the interpretation must to be internally consistent. It must intersect in line. Okay. So at the right side here in the picture, you can see this is the indication of fault at X line 1661. This is the fault shadow, if the fault is to the left side, so we can see that the fault shadow is at the right side. This looks like triangular here. Okay, and then the second fault indication here is offset in stratigraphy marker. So this one is, this looks like there's displacement. As you can see here, the line is a little bit separated to each other. So this is what we say it is offset in stratigraphic marker because of the fault itself. Okay, next. Okay, the next one is the fault in surface map. So this is what we get, and the information about the fault that we have identified. So there are altogether 6 faults that we have been observed in the horizon F, top F horizon. So all the fault is normal faults, and only one fault, which is fault 5, which we pick at inline, okay, because it is perpendicular to inline, so that's why we pick at inline line, okay. And then here is the tip and the azimuth of the faults. So as you can see here, only the later on, after that, when I explain, it's quite difficult to find fault F because fault F is not cross-cutting the top F horizon. So that's why it's quite difficult to identify fault F in top F horizon. Okay, next. Okay, next is the fault in 3D. So this is the fault plane. What I said earlier, you can see here the fault F here is not cross-cutting the top F horizon. So that's why it's quite difficult to identify the fault in the top F horizon. Okay, next. Okay, next is the fault picking in 3D. So this one at the left side is TWT, while the right side is at the depth. The depth. Okay. And then the fault picking in 3D is actually, this one is not the fault plane yet. This one is only the picking that we do before we generate the fault surface. Okay, next. Okay, the next one is the difference between surface map for TWT and depth map. So as you can see here, it's not a big deal. It's not a huge difference here. Okay, the depth maps are compatible with the time maps. Nevertheless, there can be subtle differences because of velocity variations that would give rise to the departure of image phase from the vertical. So the surface map TWT is, the range is quite low compared to the surface map depth is actually. So if you can see it clearly, okay, it's not a big difference, but only a little bit. It's only a little bit different between the surface map for TWT and the map. Only the elevation is different for the MQT elevation. Okay, next. Okay, we have done with fault, then we move to the channel in seismic delta. So from the picture here at X line 3640, we can observe that there is channel, which is indicated by U-shaped seismic line. But nevertheless, at top F horizon, it's quite difficult to identify the channel due to the low resolution at the distal layer. So that's why we refer to the, if I'm not mistaken, this one is E32 horizon. So it looks like there is loading here, like basically like U-shaped small space here. Then that's why we would assume that at this line here there is a channel. Okay. Next, after that, after we're done with horizon picking and then we're done with fault picking, then we move to the velocity model. So before we do the velocity model, we have to do TZ curve. So this is what we get from TZ curve for Bundi 1, TWT, and also South Bundi, TWT also. So this one, the x-axis represent ND, while the y-axis represent TWT. So this is the equation, And then after we have done with the calculation and so on, then we can produce the velocity. Yeah. So I pass the floor to my friend Sherry. Thank you.
So now I will presenting about the discussion on the finding of the map generate. In this slide, we can see there are two maps, which is TWT and also the depth map. So from the map, we can see the difference between the TWT map and the depth map is the elevation. The higher elevation for the TWT map is negative 1,380, while the depth map is negative 1,410. Next. Based on the both map, we can observe that the elevation is increased toward the north and decreased toward the west and south. The red line in the map was indicate the normal fault. There is a major fault in the north-south direction with the east-west fault. Near it, left cross cut the top F, while on the right below the top F horizon. Near the well, there are three faults with a channel, which is indicated by the blue circle. The difference between the TWT map and the depth map is the elevation. The highest elevation for the TWT map is negative 1,280, while the depth map is negative 1,410. And the lowest elevation for the TWT map is negative 1,920, while for the depth map, the lowest elevation is negative 2,190. Next. Next is about the hydrocarbon indication or amplitude anomaly. In the picture, we can see the level of the bright spot, dim spot, and also the flat spot. The bright spot is the spot with a local increase of amplitude associated with hydrocarbon that height due to the increase of the RC by a gas in a pore space. Impedancy contrast at the top of the sand increase which make a reflection stronger and more negative or brighter. The dim spot is highly consolidated sand. The velocity and the density decrease due to the hydrocarbon to the pore space but will not decrease enough to reverse the polarity of the RC. The hydrocarbon reduce the acoustic impedance and RC, then the dim spot will produce. Flat spot is like the gas oil or oil water or the gas water context. The flat spot caused by the low saturated gas in the reservoir. Next. So, based on the literature review, Bundy 1 and the South Bundy has hydrocarbon potential which is dominated by the gas. We can verify it by looking at hydrocarbon indicators such as amplitude changes on the stat station, velocity changes, wavelength changes, frequency, flat spot, gas chimney effect, structural conformity, and also the down dip limits. We can observe amplitude brightening or the bright spot on the seismic, which indicate the hydrocarbon zone, and also velocity lowering in the hydrocarbon zone. There is also polarity reversal or phase change at the reservoir edges. Chaotic zone near the fault might be the good indication of the gas well as well. From the map that we get, which are TWT and depth map, we can observe that 7 set of fault with channel at southeast direction. There is 3 fault near the bullfire which act as trap and migration path from source rock to the reservoir. Furthermore, top F is dominated by the sandstone, which is a good reservoir rock. Next. Next is a problem and solution. In this project, we have problem and also we came out with the solution. First is synthetic generation. The problem that we face is to produce synthetic seismogram on petrol. This problem might be due to the error in data collection or the software itself. Therefore, we skip the synthetic generation process and continue with the horizontal picking. Next is a weaker seismic signal with depth. Top F is deeper compared to the East 32. Therefore, the seismic signal is not It's not as stronger as E32 and it is quite difficult to do horizontal picking manually at the top F zone. Therefore, we use CD 2D auto track to make it easier to be picked. Next is velocity model generation. To generate the depth map, we need to use velocity model to convert from TWT map to the depth map. The problem that we encounter to do the velocity map is the data error of the Bundy 1 and the sub Bundy well. Therefore, we ask help from the GA. By using her computer, we can generate our velocity model. Next. So for the conclusion, the seismic interpretation can be done using the Petrol software. We can implement the main goal of this project, which is to evaluate the geological structure subsurface in the Bundy field by using the Petrol software. From this project, which is on the Bundy field using Petrol, we are able to generate the subsurface map by collecting seismic data and well data. To do the horizon and fault picking and also the interpretation, and producing the time and depth map of the top F by interpreting the horizon and fault. The outcome of this project has contributed to the further understanding of the development and exploration in our study area. Next. So before we end our presentation, there is some quote from the Adam Sedgwick, which is, we cannot take one step in geology without drawing upon the homeless straw by the bygone time. So that's all. Thank you. This ends our presentation.